All right, thank you very much. It's great to be back here. I really enjoyed the last time I gave one of these, and I'm looking forward to hearing what people have to say again. So I'm going to be talking about galactic archaeology. This is what we can learn from studying stellar fossils around us. So learn about the early universe or earlier times in the universe by studying the very nearby universe. And since I did put archaeology in the title, I feel like I will have to refer to Indiana Jones at some point, so I promise that will show up somewhere. Right, okay, so I'm a cosmologist. What I study is the universe, apparently. So the goal of cosmology is to understand our universe, its contents, and its evolution from the beginning through the present and into the indefinite future. So if you're doing it, it pretty much is encompassed by cosmology by this definition. But really what we're trying to understand is the evolution of cosmic structure, how galaxies that we see here in an image like this would have formed, how they evolve, where we came from, where we're going. So there are a couple of options for this. The first option is to become a mad scientist. So you want to build a time machine, then you can understand the universe very well. You can go to all the epochs of the universe and look at that. So I decided to use my favorite research tool, Google, to see what a time machine would look like. Apparently it looks like kind of Chris Angel in a tunnel trying to find an alien. I'm not sure what's going on there. The second most popular hit is a really messed up Santa's sleigh, I guess. I don't really know. No. So Google may not know exactly about a time machine. We're still working on this technology. Talk to me afterwards if you want to know more about that. So, you know, I don't like working hard, but I'll try to become smarter and use the tools that we have at our discretion. And that tool is the time machine that the universe already provides us. So the universe is a time machine in the sense that we're sitting here at around 13.8 billion years after the start of the universe. And as we look back, we see light from various different events that happened at various different times in the universe. And the reason for that is that light takes a finite time to travel from anywhere to come to us, okay? So the further away we look, the further back in time we're actually seeing. So for us, the universe actually really is a time machine. And this is what I want to use to study galaxy evolution and what many people use. So if you want to understand the earliest epochs of galaxy evolution, you have to look as far back as you possibly can. So we build more and more powerful telescopes, bigger and bigger apertures, more and more sensitive equipment, and we can reveal tremendous and exciting things about these earliest epochs of stars and galaxies. We've actually pushed our frontier back to maybe around even a few 100 million years after the Big Bang to the first galaxies is what we're really trying to do with direct observations. So in this picture of the universe as a time machine, we can think of how long it takes for light to get to us, and that tells us how long ago that light was emitted, how far away we're seeing. So for example, the sun, it takes light 8 minutes to travel to us from the sun. So the sun may disappear in 7.5 minutes. Don't bet on that, but we wouldn't know, all right? Pluto, everyone's favorite dwarf planet, takes 6 hours for light from Pluto to reach us. Okay. Our nearest large galaxy neighbor, the Andromeda Galaxy, M31, maybe your screensaver on a Mac computer, I'm not sure. Whoever made this image is probably rich by now, or very angry, one of the two. Light takes 2.5 million years from Andromeda to reach us. And this never ceases to amaze me. This is the nearest big galaxy, and it takes 2.5 million years for light to come from that galaxy just to reach us. This is one of the biggest clusters of galaxies in the nearby universe. So nearby is relative here, right? This is 326 million light years away. But this is one of the nearest big clusters, and it takes light 325 million years from that cluster of galaxies to reach us. And if we really push things back to as far as we can see, the earliest galaxy that we know of is here at around 13.4 billion years ago. So just a few 100 million years after the start of the universe, after the Big Bang. It's not a real looker, but it's very interesting to study, okay? So how do we find these things? Well, we look at very, very deep images, and by deep images, I mean the Hubble Space Telescope stares at one patch of the sky for an extremely long period of time, and then extremely smart people go in and they find some little smudges here. You study those smudges, and you figure out, in a way that I'll talk about later, that that has to be a galaxy at very early times in the universe, okay? So this is about how big a field picture that Hubble can take at any given time. And it looks pretty impressive if you look at that. There's a ton of galaxies here, right? They're at all kinds of different distances, so light has taken all kinds of different times to reach us. But I think it's important to get a sense of scale. If you compare that to the size of the full moon, that's how big the Hubble field of view is. So when you see a picture from the Hubble Space Telescope, you're seeing something that's about this size typically relative to the size of the full moon. It's a very small portion of the sky, and it's a big universe out there, right? In fact, some of the nearest galaxies are much, much, much bigger than this. This is a galaxy that's very nearby, again, relative, 500,000 light years away. It's actually within the edge of what we think of as the Milky Way. And it has, again, a puny sort of 50 million stars. So a typical galaxy like the Milky Way might have 100 billion stars. So this is a small galaxy. And we'll hear more about these in one of the talks later today. But you can see that remember, we were looking at one tiny smudge in this tiny image here and trying to understand all kinds of things about it. If you look at this image, there's a tremendous amount of information. So by studying the nearby universe, we think we can maybe understand things a little bit differently. Okay? And in fact, there are even fainter galaxies in the nearby universe. This is a galaxy that's 100,000 light years away and has just around 5,000 stars in it. This is incredible. In fact, if you look at this galaxy, here they've tried to mask out some of the bright stars that are in the foreground of this image. If you actually look at the galaxy's stars itself, it looks something like this. Okay, so in the very nearby universe, we can actually see things extremely well. Being so close really helps out. So what we can do is use this as our time machine. Okay, so rather than studying fossils in the sense of looking at the very early universe directly, so rather than studying galaxy evolution by directly looking at the first galaxies, we can try to look at their fossilized remains in the very nearby universe. So these tiny galaxies that we saw around us today that look to be extremely old. Okay, so we can really understand a lot about these systems just by looking at the nearby universe, not having to go very far away. And one of the really exciting things about this is that we can observe and study objects that are extremely faint. So these things aren't just way too faint to be seen by Hubble Space Telescope. They're even probably 10,000 times too faint to be directly seen by the James Webb Space Telescope, which is going to be launched in about a year and a half and is Hubble's successor. Okay, so we'll never see galaxies like this directly in the early universe, but we can see their remnants around us today, and that means we can understand the early universe by understanding these galaxies today. And that's the reason for calling this field galactic archaeology. Of course, another reason is that we all want to be very cool, like the famous people of the screen, right? So there's an extremely well-known professor by day who goes around solving lots of mysteries by night, getting into trouble, getting out of it, and we all want to be like that person. Who am I talking about? Of course, it's Ross from wait, sorry, this might be, no, we're talking about Indiana Jones, right? That's the real idea of an archaeologist. So when I think about this, when I say I'm a galactic archaeologist, I'm kind of daydreaming that I'm out there, avoiding the boulders and not being run over by anything. So apparently my Photoshop skills aren't as good as our MCs, but I do better than him with the sand. That was like way too little sand. I'm sorry. Okay, so how do we do this? How do we understand the very early universe by looking at very nearby stars? Well, the basic idea is to use what we'd call stellar spectroscopy. And that's just a fancy kind of way of saying that every element has a unique chemical fingerprint. So there's a unique set of atomic transitions that correspond to every element, and we can look at a spectrum of a given star and try to find out what is in that star by looking at this chemical fingerprint. Okay, so here is an absorption spectrum from hydrogen. It has very specific absorption lines, and we understand very well why the lines only have these transitions, so why there is light everywhere except at these very specific wavelengths. Okay? And if you look at lots of other stars, these are actually real stellar spectra. You can find a variety of stars, and they have different kinds of absorption spectra. The main point here is all of these elements, they have different chemical fingerprints, and by understanding those fingerprints, we can understand the properties of stars, the elements that are in those stars. How much of that star is made up of hydrogen? How much is in helium? How much is in calcium, maybe? Okay. So that also makes me, besides being a part-time archaeologist, I'm also a part-time detective. And you know, I do spend a lot of my time looking really confused and maybe a little scared at what's in front of me, but that's normal. Okay. So our tools for this, well, what are our tools? Everybody's familiar with the basic periodic table, the sort of building block of a lot of chemistry, right? Astronomers have their own version of this. It is much simpler. It looks like this. You know, there's hydrogen, there's helium, and there's a bunch of other crap out there. So, all right, it's a little coarse, but we'll talk about why this is the nomenclature. So, but we do have our own version of the periodic table. And the periodic table for us is where the elements actually come from, okay? So how do we understand these elements? So we want to understand the origin of elements around us in the solar system. So let me walk through this a little bit. At a fraction of a second after the Big Bang, protons became stable. And about a few minutes after the Big Bang, protons started to fuse together to form helium. And for the next few 100 million years, the universe was a very boring place in terms of nucleosynthesis. The universe's chemical composition was completely constant. Okay, so the only element besides hydrogen that is made in the Big Bang directly is helium and a very, very trace amount of lithium. So that's why we call everything heavier than helium metals, okay? These are the things that were there at the beginning, pretty much, and everything else kind of came later that we're trying to understand. So everything after this came from stars, pretty much, or the explosions of stars, which is amazing, and this is why Carl Sagan says that we're all star stuff, right? Everything, all of the metals, everything that's heavier than helium came through a star in some way. So a couple of elements are not exactly like that. They're elements you don't see very much, so lithium, beryllium, boron. Some of those come from actual cosmic ray collisions in our atmosphere and the atmospheres of stars. But now, once we start to get to things like oxygen and aluminum, magnesium, okay, these elements, they all get released during the explosion of extremely massive stars. And so this is where every element of oxygen in your body really came from the death of a star that was originally more massive than around 10 solar masses. And this is how we understand the periodic table as astronomers. If you look at slightly more heavy elements, you find that these come out in the explosive deaths of less massive stars, okay? So dying low-mass stars or exploding white dwarf stars, which are remnants of intermediate mass stars. These are the things that produce all the elements you see here. So manganese, iron, nickel, cobalt, zinc, everything there is coming from these low-mass stars that end up exploding or releasing their metals later. And everything else, pretty much, requires an extremely rapid process of neutrons bombarding one another, okay? And that requires, we think, the merging of extremely massive neutron stars. So this is a kind of a crazy event. Neutron stars themselves are kind of amazing. A teaspoon of neutron star material weighs as much as a mountain, okay? And you smash two of these things together, and you get a lot of gold out. So, you know, I don't have step 2, but step 3 is definitely profit in this chain. But so everything heavier here came from something like the merger of two extremely heavy neutron stars. And a crucial information for us who are trying to do galactic archaeology is the timing of this. Because stars have very specific relationship between how massive they are and how long they live. So the most massive stars burn through their nuclear fuel extremely quickly and die very fast. So exploding massive stars happen very quickly after star formation begins, within the first maybe 10 million years. Okay, remember this is short on a cosmic time scale. I know it sounds kind of insane up here, right? But the exploding massive stars are coming in the first 10 million years after a star formation event. If we look at dying low-mass stars, those take a very, very long time, so billions of years, 10 billion years, even more sometimes, to release some of the metals and the elements they have back out into the universe as a whole. Exploding white dwarfs actually kind of happen continuously after an initial delay of a few 100 million years. And merging neutron stars, again, are a very exciting topic of research, and we don't actually know that much about that. So if anybody's got good ideas, I promise not to take all of the credit for them, just 95-ish%. Okay, so if we look at the Milky Way, one way we can try to do a diagnostic, really study the fossils in the Milky Way, is study when those products from the massive star explosions come out. So remember, the massive star explosions are happening very, very early. And all the other metals are coming out much later, okay? So if we want to look at when the massive star explosions happen relative to when all the other metals come out versus when everything is produced, we can just imagine taking a box of hydrogen and helium, allowing it to form stars, and asking what will happen. Well, very early in a galaxy's life, it'll live up here because it won't have much in the way of anything beyond hydrogen and helium. The stars won't have lived long enough to produce those elements. But what few stars have produced them will be very rich in these elements from massive star explosions. Okay? As you go on later and later in a galaxy's life, as long as star formation happens long enough, you continue to have these massive star explosions, but you also have all of these other elements that come in, and well, we have two words for this. One word is pollute, and the other word is enrich. So you can tell that there's some kind of tension here a little bit. But no matter what you want to call it, the stars come in, the elements come in, and they contribute to the subsequent generations of stars. Okay, so the first generation of stars could have only had the elements that are there at the Big Bang, and progressively you are able to have more and more of these heavier and heavier elements incorporated into stars as long as you're able to continue to form stars. So if we look at the Milky Way, or a galaxy like it, right now it's maybe forming 1 to 2 stars per year. And over its entire lifetime, well, it's a little more active in the past, maybe it's formed 100 billion stars in total. So if we look at what the Milky Way should look like, we'll see a broad mix of ages. Right? There's stars that have formed over this entire period, so they're massive star supernovae going off everywhere here. There are other low-mass stars that have been able to die and release their elements into the gas and being reincorporated into future generations of stars. So we see all kinds of different ages within the stars of this kind of galaxy. Now here is the same kind of diagram for one of the faintest galaxies that lives around us. Rather than forming 1 or 2 stars per year, this galaxy well, would probably be fired by your president or various other people. So 1 star every 10,000 to 100,000 years. So maybe only 1,000 to 10,000 stars in total. Okay, this is kind of incredible to me. Furthermore, all of the stars seem to have been formed within a very short period in the very early universe. Okay, so if we look at this galaxy, we see all of the stars that we can see there are old, and they mostly reflect the chemical composition of the early universe. That is, on the diagram like this, the faintest dwarf galaxies have almost no metals. They have 100 times fewer of heavy elements compared to what we'd see even in something like the sun around us today. So that's pretty amazing. But this means not only can we look at the early universe and processes there by looking at these faintest galaxies, we can also really understand a lot more about how these massive stars explode, because those are the only products that are reincorporated into the galaxy's stars in this kind of system. Okay, so if we look at Milky Way satellite galaxies, this is the known satellite galaxies of the Milky Way as a function of year. It started out with 2. Okay? And pretty quickly, by the 1960s, there were a handful. We've now basically made it to 1995. There's 10 or 12. And in the past, say, 10 to 12 years, there's been this complete revolution in our understanding of these small stellar systems around the Milky Way. Okay? And this is, again, based on better telescopes and an understanding that we should actually go out and look for this stuff. And all of these things that you see in red and in green, these are extremely, extremely faint galaxies that are very consistent with having formed all of their stars extremely early in the universe. And what we'd really love to do is go back out and examine all of these. Okay? But part of the problem that we have with doing that is the stars in these galaxies are inherently very low mass. That's why they've survived till today. And that means they're also very, very faint. And so if we want to go hunt for these fossils in the night sky, we're trying to look at systems like this, okay, and figure out what's happening to the light in galaxies like these, which are not going to win anybody's poster competition for a galaxy, I don't think. But this is all about to change, I'd say. Texas is very much invested in a new generation of telescopes. The giant Magellan telescope is the one that we're working on. And, okay, it's kind of a big picture, but it's hard to get a scale here. There is a person right here that is set for scale. Okay, so this is a 24-meter aperture telescope. The current best telescopes are sort of 8-meter class. So this is going to be 10 times better in terms of the collecting area. And that means we can really, really, really see much, much fainter stars. So this is a very bright dwarf galaxy. We can actually measure properties of maybe 1,000 stars in this. With this kind of telescope, we should make something like 10 times more than that we can study. And for those very faint galaxies, something like this, we should actually be able to get information potentially about every single star in this galaxy if it's near enough to us. And that means we'll be able to know everything about this galaxy's history just by studying the stars that are left in it today. We'll say this supernova went off then, there was this much mass that got released at that point, it got reincorporated, somebody painted them blue and red, all kinds of things happen. So for people like me who fancy themselves a little bit of Indiana Jones but also have to have a real day job here, this is tremendously exciting, and we're all really looking forward to this giant Magellan telescope to understand more about the very distant universe by studying its fossilized remains very nearby. So I think just to wrap up, some of the biggest questions that we have in cosmology and the formation of galaxies evolved the very earliest epochs. And those are the hardest to see, right? They're the farthest away, the faintest, and therefore the hardest to really probe directly. We don't have that time machine yet, unless Chris Angel has something that I haven't heard about. So tremendous progress is being made in directly observing the very early universe. But some of these galaxies that are in the early universe are just so inherently faint that we'll never be able to see them directly. The only way we'll be able to understand the very first galaxies, probably, is by looking at their remnants around us today, by looking at these galaxy fossils. And so I think that's where this idea of the stellar fossil record, or galactic archaeology, is really exciting. And to me, the understanding that the smallest galaxies that are extremely nearby may tell us something fundamental about the very first galaxies and the early universe. And I didn't get into it today, but a lot of my research is on the nature of dark matter. This is really tremendously exciting to me, and I think we're in an era where we can really start to understand these things. So thank you very much for your attention.
All right. Thank you, Director of Dark Matters. So we'll take questions from the audience. All right, first one up right there.
This is a great talk. I just want more confirmation to see if I'm drawing the right conclusion. If you're indicating that these galaxies evolving are the Earth.
So the question was, if I'm saying that these very ancient and low-mass galaxies really reflect the primordial composition of the early universe, if I sort of extrapolate forward, would I be saying we should be seeing new elements that might actually, we've never seen around us today, but that might be produced in the future? And I think, unfortunately, the answer is no. Pretty much any star that any process that we can understand in a star has already happened in the universe. There was a time when that would have been the case, but that would have been very early on. As soon as the first normal stars started to form in the universe, all of the heaviest elements that could have been out there were eventually produced in those stars or their explosions. But never say never, so we can always hope. But I think it's unlikely to be the case.
All right, another question in the back. Yep.
Do we know when the oldest evidence we have?
So the question is, what is the oldest period at which we have evidence for dark matter, and what can that actually tell us about dark matter? So I've been talking a lot about the era of galaxies. This is maybe starting at 500 million years after the Big Bang and all the way forward. We have extremely strong evidence for the existence of dark matter at 380,000 years after the Big Bang, well before any galaxies could have even formed at all. So there's actually evidence for dark matter at very early times, and the reason for that is structures that we see around us today just wouldn't have been able to grow into what they are without some kind of dark matter. And that does give us very strong constraints on some of that dark matter property also, because in the very early universe back then, radiation, so light, was much more energetic than it would have been today. And so if dark matter had any kind of interaction with light that was very relevant, we'd see it happening then more strongly than we do around us today. So that's some of the strongest constraints we actually have on how much dark matter can interact with normal matter. And it doesn't. Yeah.
Okay, other questions? Right up front.
So the question is a very good one. The question is, I said, for maybe some of these small galaxies with the next generation of telescopes, we might be able to understand every single star in that galaxy. And would that mean we'd understand more about that galaxy than our own? And I think actually the answer is yes. Our galaxy is somewhat complicated. As I showed earlier, it's formed stars over a lot of times. It's probably had other galaxies that have merged with it. There's lots of complicated processes that we think have gone into building up our galaxy. Whereas these things really probably just had a starburst that lasted, well, burst is very relative here, a very low-level episode of star formation for a few 100 million years, and that was it. And so we can really understand that thing maybe even better than the Milky Way. But there are lots of surveys that are really going to increase our understanding of the Milky Way as well.
All right, let's do two more. Well, this gentleman first.
So the question is related to looking for intelligent life, and the question is, if we can actually see these fainter stars, would that actually increase the chance of seeing intelligent life? As far as I know, it's not really clear that that would be the case, but I think the more we understand about these low-mass galaxies and the more we understand about the stars in these kinds of systems, the more we will know whether the conditions for life are met in some of these systems and not. And again, that's easier to study much closer. The first place you look wouldn't be as far away as possible. It would be as near as possible. And so going fainter and fainter is very good for that kind of thing, absolutely.
Our next speaker will probably get into that as well. All right, last question right there.
Your chart on the
So yeah, that is a good question. So he was saying that basically he's seen similar charts of our astronomer's periodic table, not the lazy one that had 3 elements, but the one that had a bunch of elements. And he was saying that he thought everything heavier than iron and those came from supernovae, not necessarily from merging neutron stars. So the merging neutron stars can create a supernova, so it's a question of what you're actually calling this, and is the origin of this kind of supernova from 2 merging neutron stars, or is it from some other kind of source? And a lot of evidence that's come up recently really says that it's not just a sort of a normal supernova. It has to be really, really neutron-rich material. And actually, these dwarf galaxies are one of the places that's been some of the strongest evidence. But people are still researching this, and so that's an active topic of debate, I'd say.
All right, let's thank Director of Dark Matters one more time.